Hello, Samuel here. Today we are going to do the first Abinit tutorial together. So I go on to the abinit.org webpage here and I'll click on tutorial. So today we are going to focus on the first tutorial, but if you start with Abinit, I recommend you to do at least the four basic tutorial, namely tutorial 1, 2 and 3 and 4. And today we are going to focus on the first one. So I will click on it, and this tutorial is focused on the study of the H2 molecules and also at all the convergence study that you need to do in order to have a physical meaningful result. I'm gonna spend a little bit of time also explaining some of the physics behind it, but I'm expecting you to have a certain background into density functional theory. So what Abinit does, it's a first principle solver, so it will solve the Schrödinger equation. So it will solve this equation here, where you can see that you have the n-body wave function, and here you have this operator, which consists of a kinetic operator, an external potential, and the electron interaction. Here we already have split the problems into two parts, so solving the motion of the nuclei of the atoms, and here we're solving only the electrons around the nuclei, and we assume that the electron will rearrange instantaneously when the nuclei move. This is named the Born-Oppenheimer approximation. So we decouple the nuclei and the electron dynamics to make the problem easier to solve. But still this problem is very complicated, and a way to simplify it is to use the density functional theory. This theory has been introduced by Hohenberg and Kohn in 1964, and also followed by the Kohn and Sham theorem 1 year later. And what they are doing, they are casting this n-body system, this n-body wave function, into a series of non-interacting wave function, which are much easier to solve, and they have proven that this was equivalent if using the exact functionals. So today we are going to solve this Schrödinger equation in the density functional framework for these H2 molecules. So if you already have installed Abinit, you can go into the directory. If not, I have made another video on how to install Abinit, and you can check it out. So assuming you already have installed it, you have all those directories. So normally your installation is made into this build directory. So you will go into the tests here, tests, and then inside it you can see that you have tutorials. I'm going to it, and then into input. And here you have all the basic tutorials plus some other. So the basic tutorial are the T-base, those T-base 1, 2, etc. You can there create, for example, a work dir, so like this, and then you go into it. Okay. So that's what they advise you to do in the tutorial. So to go into this input stuff to create the working directory, and then you can copy all the file above. So I will do that. I will copy the tbase.1 and all the tbase, so that we have all the required files for the first tutorial. So I have them all here. And then we're gonna look at the first input file, this tbase1.in. And now I'm going to go through all the important input variables. So when you're looking at an input files and you're wondering what the input variables mean, So in the tutorial you can see that you always have some explanation, some commentary that will not be read by the ab-init software, and that usually explains you what the variables mean. But if you still have doubts about the signification, you can always go onto the ab-init website here, and then you can go to input variables. And here you have a complete list of all the input variables. So that's a very handy web page where you want to go. So for example, the first one is this a cell variables. So it's written here that the keyword a cell refer to the length of the primitive vector in bor. So the bor unit. So inside ab-init we use bor for the length. We use so we don't use angstrom. We also use artri instead of the more commonly known electron volt. And so we can go into this input variable list, and we can see, for example, the a cell variable. So I click on it, and you have a number of extra information. So it tells you that it's in bor unit. It tells you that it's the unit cell vector, as commented here. And in order to define the primitive cell that you will be using, you need usually two variables, this a cell and then another one. So usually you will use r prime. So r prime is the vector in Cartesian coordinates. So the first vector is along the x direction, the second one is along the y, and then the z. And this line is commented because it's the default value, but you can enable it and it will do the exact same. And then you will multiply this vector by the a cell. So you have the vector times 10 to say that it's 10 bor. Okay. Then we want to define the atoms. So n types tells you the number of different types of atom you have in your calculation. Here we are doing only the hydrogen. So we only have hydrogen. So we have only one type of atom. And then we give the nuclei, the Z nuclei value. So hydrogen is the first one in the periodic table, so it has the value 1, so we put 1. And then, since we're doing H2, we have 2 atoms, so we put the number of atoms is 2. And then we put the type of atom for the first one and the type for the second one. So, for example, if you would have done NaCl, for example, you would have 2 types of atom, and the first one would have been the Na, the sodium, and then the second one would have been the chlor. But in this case they are both hydrogens, so the type for the first one is 1, and the second one is also 1. Then you put your atom into Cartesian coordinate. It's also possible to put them in reduced coordinate, and then you will use the x-red variables. And here we have put the first hydrogen atom in the minus 0.7 bor in the x-axis, and the other one on the other side. We have then the cutoff energy variables, and I will come back a bit to explain what these variables really is. Then the number of K points used to sample. We only have 1 K points because this is an isolated system, so you can see that we have taken quite a large box. So the distance between the two atoms is only 1.4 bor, but the size of the primitive cell is 10 bor, so it's really quite large. And you have to do that because you want to compute molecules. And since we are using a periodic code, the primitive cell will be replicated into each direction. And if you want to compute molecules, you don't want interaction because you want to compute only 2 atoms in a vacuum. But with this code you cannot really have a pure vacuum. You will have replicated cell, and if you want to mimic the vacuum, you will do a very large cell so that the 2 atoms in the center of it will not interact with the replica of the cells. And you need to make a convergence study. If you want to study molecules with ab-init, you need to make a convergence study on the size of the primitive cell you're putting your atoms into it. So you want to increase, for example, this cell size and see if any of the property you're studying do vary significantly or not. And if you can see that the variation becomes smaller and smaller, you can at some point say that you're converged and the value of the box is sufficiently large for your calculation. And then we have to give some self-consistent procedure criteria. So the way ab-init is solving the density functional problems is by doing a self-consistent cycle. So it will try to find a solution in an iterative way, and we have to set a number of criteria to stop the self-consistent procedure. So here the end step says that ab-init can at maximum do 10 self-consistent cycle, and if it didn't reach the solution at that time, it will just stop the self-consistent calculation and it will continue, and it will also raise a warning if you did not get the required precision value that you have set. In this case, we have used the TOL-DFE, which is a tolerance criterion on the total energy. So if twice in a row the total energy differ by less than 1 to the minus 6 R3, then it will consider that the self-consistent procedure is converged, and it will stop the self-consistent procedure. And this DMAC variables is not extremely important. It's to set the model dielectric function, to precondition it to a certain value, and this will help the first self-consistent cycle. But if you change it slightly, it will not really affect it. It might, for example, take a little bit more time if the value is far from the optimal one, but this is not very important, so I will not focus on it. Okay, so now I'm going to explain a bit more these ECAT variables. Okay, so before explaining the ECAT variables in ab-init, I must explain the block theorem. Because we are working in a periodic solid, our one particle Hamiltonian must be periodically invariant with your lattice system. So you can express the wave function, the one particle wave function, as a product of a periodic function u and k times a plane wave function e exponential of e k dot product times r. And if you are working in real direct space, you also want to be able to work in reciprocal space. So for this example, you can see here that I have an FCC lattice, phase-centered cubic lattice, and my direct real lattice is given by those three A1, A2, A3 vector, and those vector will give me the irreducible smallest possible primitive cell. And you can define the reciprocal lattice with this equation. So the g's, which are the reciprocal lattice vector, are defined as g scalar product times the a, so the direct lattice. If it's equal to 2 pi delta eg, then the g's are the one you are looking for, which are the reciprocal lattice. So once you have your g's, you can define your g, you can define your gi, and those are the g are in reciprocal space your direct counterpart. And you can then make an expansion of the plane wave, so the periodic U's can be expanded into plane waves. So you can expand your U and K in terms of a sum of C coefficient times this exponential, where you can see the G's here. Those G vector are an integer times the G1, G2, G3 that are defined with this relationship. So, for example, if you want to define to reproduce this 1D function, you can see that this is a complex function that has the periodicity of the lattice, so you can see that it's reproduced here. And we are only, so for the periodic U, we are only concerned about describing the irreducible cell, so only this one. And we're gonna try to mimic to reproduce this complex function with a sum of more simpler function, namely the plane wave. So it will be a sum of those function. So the first plane wave is the one with the smallest integer. So it will be, for example, 1, 0, 0, and this will give you only one parabola like this. And then you have the second one with L equal 1, 1, 0, and this will give you one node. And then you have 2 nodes and 3 nodes, and it will, so a node is when you cross the y equals 0 axis. And you can see that the more plane waves you have, so the more wiggling plane waves you are, if you make a sum, this will allow you to describe more accurately this complex function. So you can see, for example, that this function has some quickly varying wiggles, and in order to describe those wiggles you will have to use plane waves that oscillate also quickly. So this means that the more complex is the function, the more plane wave you need to have in order to describe your function accurately. And this is what the ecut variables is all about. So this periodic function, so in reciprocal, so in real space, expressed as this sum over g's, can be put inside the wave function, because if you remember, the wave function is this periodic part times e exponent k e k r. So you can see that this one will add up with the other one, and you end up with this function. And in ab-init we define the energy cutoff as a kinetic energy cutoff. And how do we define that? Is in the Schrödinger equation you have the kinetic operator, and when you apply this operator onto the wave function, you will derive the wave function with respect to a position r. So you can see that the k plus g, I k plus g, will go down once, and since it's you derive twice, it will go down twice, and that's why you have this k plus g square, and the I will be I square, which is -1, so you have the minus that disappear and become a plus. And then you have this value. And in ab-init, the cutoff energy E cut, so the variable E cut, is defined as the maximum, so the biggest G you can take, such that this inequality is verified. Namely, the k plus g square divided by 2 must be smaller to the variable E cut. And this is how you define your E cut. So if we look at the ab-init input variables in the tutorial, you can see that your E cut here it's equal to 10, which means 10 R3. And this means that it will take all the g's such that k plus g squared divided by 2 is smaller than 10 R3. Okay, now that we know a little bit more the input variables of ab-init, we can actually do the calculation. So following the tutorial, so we already copied all the base file, and we can issue the command. So the way ab-init works is it has this file files, which we can look into it. So we can look into it, yes. So it gives the first line contains the name of the input file. So in my case, since I've copied, it's in the current directory, so I don't need to put the dash dash the dot dot dash. I can just put it. Then you have the name of the output. So there is an X because it will be used for the different input throughout the tutorial. So I will put 1. This is for the information file. Information will be issued there for the next input. The output file will have this format, and this is all the temporary file will have this format. And then you have to give the path of the pseudo potential used. So here we are using the GTH pseudo potential for hydrogen that is located into the ab-init distribution under the pseudo potential for tests. So that's the way the files are constructed, and you need to pass this file to ab-init. But first you need to use the executable for ab-init, so I need to go up because the executable is not in my current directory, so I need to go up quite a little bit. Yes, so here is the first path of all in my main directory, and as you remember, I've installed ab-init into this build directory that I have constructed. Into there you go into source, then 98, and the 98 main contain all the executables, and it contained also of course ab-init. So here is the ab-init executable, and then I need to pass the file. So I will do that. I pass the file, and then you can launch ab-init. But a good way is to redirect the output like this, and you can, for example, call it the log file, so it will redirect the output into the log file, and then you can issue. So you can see the calculation went very quickly because it's a small calculation, and then it creates a lot of new files. You can do into the log file, and it will contain a lot of information, but I will go into it later. But first you can see that you have the output format, so you have the database file, you have the density file, and the eigen. This contains the eigenenergies, and this contains the eigenenergies. It's the same file, but it's in the netcdf file format. And then you have the output file into netcdf file format, and you have the standard output file following the name that we gave into the file. And finally you have the wave function file. This is usually a huge file, and you may want to remove it quite quickly because it's a huge file, and it contains the wave function. So if we go into the output file, you can see that you have the version, then you have the symmetries, so the symmetry of the system. So ab-init computes the symmetries, and it tells you that the symmetries is P4MMM, is the 123 space group. It's a primitive tetragonal, and then it gives you the value of some input variables that you didn't set necessarily. Some are default and some are calculated. For example, here you have the number of symmetries for your system, so you have 16 symmetries. You have the number of atoms that is reported, 2 atoms, the number of FFTs, you have the fast Fourier transform, you have the number of k-point. This is important, the maximum number of plane waves. So this value was set with the eKit parameter and the ACL, so it's a combination of both. It will give you the maximum number of plane waves you have. This is the maximum number of bands. Okay, it will then give you an estimation of the memory required, and then it will output all the variables you have inputted. It will also add the value of the input variable that you didn't set but that were taken as the default variables. So you can see that this is what is written in the tutorial. So you have all those output file, and then you have the output that look like this. Then I already spoke about those variables: A cell, the number of type of atom, the Z nucleus, the number of atom, the type of atom, X cart to define the Cartesian position of the atom, the cutoff energy, the number of K points, the number of steps for the cell consistent cycle, the tolerance of the stopping criteria for the cell consistent cycle. So it's the stopping criteria on the tolerance of the total energy, and the Dmac for the dielectric criteria. So when you look into the output, it will give you a lot of information, and we can go through it. So this is the real space vector. So 10, 0, 0 is the first vector, 0, 10, 0, 0, 0, 10, and then you have the reciprocal one, which is this vector. And then you have the unit cell volume, you have the angles between your three vectors that are also computed. It will report the pseudopotential, and it's a Goodacre tether-Utter pseudopotential. It will give you the header of the pseudopotential file. And then you can see that you have the summary. This is really important. So this is the summary of the self-consistent calculation. So you can see that it took six self-consistent cycles to be converged, and you can see that this is a total energy in R3. You can see it decreases, and you can see the delta. So the delta between the previous self-consistent cycle and the one you're considering is also decreasing. And once you have reached the tolerance, which is -6, but 2 times, then it's considered that you are converged. You have the residual. You have all other very important. This is the residue on the potential, difference on the maximum force, and you can see all those variables into the input variables. Then you have the Cartesian component of the stress tensor in R3 per Bohr, which means the force that will be act upon the atoms. So you can see it's quite substantial, because the atoms are not in their equilibrium position. We force them to be at those positions. And later in the tutorial, we will move the hydrogen atoms, and we will recompute the total energy, and you will see that the total energy will decrease and will form a curve. And at the minimum of this energy, you will also have the minimum of the forces, and then the component of the stress tensor will be much lower, typically -8 R3 per Bohr exponent 3. So it tells you that the iterations are completed, and in that case the convergence is reached, but it's not always the case. So for example, if the end step your set is lower than the step needed to converge, then it will just issue a warning. It will stop, but it will issue a warning telling you that you are not converged, but that it stops. Then it gives you the Cartesian coordinate of the force, the residue, other information, total charge density. Then it gives you the component of the total free energy. So you have the kinetic energy part, the R3 energy part, the eval, the exchange correlation energy, and all that sums up to the total energy. This is also the stress tensor, but in gigapascal. You would want ideally to be between -3 and -4 gigapascal to be really at the optimal relaxed position, and then it output the variables. It can give you some timing analysis, and then that's it. Okay, so you should also always look at the warning. So you can the warning are not always reported in the output file, so you can see that here we have 2 warnings, but they are not reported in the output file. So then you can look into the log file, then you look for the warning to see whether they are important or not. Here it's not a very important warning. It will tell you that the second and third dimension were imposed to be a multiple of the FFT, and that the maximum ECAT is slightly raised, but that's really not important. And it will also give you another not very important warning. So you should always read the warning, understand them, and here it's only tell you that the density went too small, but this is because of the box. So we might not be completely converged, but that's not really important. We want a fast calculation just to show you how to run the calculation. Okay, so that's it for this part. So we have now you should be able to answer those 6 questions. So for example, how many self-consistent cycles were needed to achieve the TOL-DFE criterion. So we saw it was 6, and the energy was likely to be more converged because of the definition of the TOL-DFE, which required that it should be converged. So we can click on TOL-DFE. It says that the tolerance of the absolute difference of total energy that is reached twice successively. So likely you will be at least 2/3 consistent cycle more converged than the criteria you set. It also gives you what is the value of the force. So we already looked at them in RT per Bohr. I think you can answer yourself the last 2 questions. You can always look at the answer at the end of the first tutorial, so it's easy. Then what we ask for this 1.2 part of the tutorial is to compute the interatomic distance, so the optimum distance. So as I told you, you can launch the calculation just changing slightly the position of the 2 atoms. So you can, for example, put them closer, a bit further apart, and you can compute the total energy. And then you can print the total energy with respect to the position or the spacing between the 2 atoms. And you will find the optimum spacing with the smallest force and the smallest total energy. And this will be the relaxed, so to say, position of your atom. So you can do that by hand, or you can also use IonMove, which is an input variable that will do this optimization using steepest gradient method or BFGS method to minimize the total energy and to move your atoms. And then you can compute the charge density. So as I told you, one of the output file of the calculation is this _den file. So by itself it's a binary file. If you open it, you will see that I will do it. There is nothing very useful when you look at it. So what you need to do is use a post-processing tool that is also shipped with Abinit. So in the main directory you have a tool that is called Cut3D, and you can run it, and it will tell you, okay, you can provide me either a density, a potential, or a wave function file. So I will give him a density file there, and then I can tell him, okay, it's an unformatted binary file, so I put 1, and then I can choose the type of output file I want. So in my case I would want an XSF file, so I will put 9. That is useful to then use it with another software, and I will call it h2.xsf. Alright, and then I don't want to shift, so it asks if you want to shift the grid. I don't, so I put no. Do I want to make more analysis? No, I put 0, and then it's finished. And I have this new XSF file. Okay. So in order to analyze this density file that I have converted using Cut3D into an XSF file, I will use the software VESTA. So there are a number of software that can read those kind of data, like XRISDEN or Gmol, but I like VESTA. So you can go onto the website gpminerals.org/VESTA, and then you can download it like this, and you can choose from the download button. Since I'm on Linux, I will download this one. I've already done it. You just download it wherever you unzip it, and then you can directly use it. You don't have to install it or anything. It's really very easy to use. So what I will do I will just link using a soft link minus. So I will do ln minus s, and then I will go into where I've installed it, into program, and then VESTA here, and you have the binary file that is there. So I do like this, and now I have the VESTA program, so I can launch it like this. Okay, it has launched VESTA, as you can see here, and then you can open this h2.xsf file, and here you have the hydrogen boxes. So it looks a bit weird, but that's because this is the primitive cell and it will be repeated. If you want to have it bigger than the primitive cell, you can go here, you can go to boundaries, and you can increase the maximum. So what I do, I just double the cell in each direction, x, y, z, apply, okay, and you can see, for example, that here I have the density, and I have the density around my 2 hydrogen atom, and you can see that I have a box of 10 Bohr around each pair of 2 hydrogen atoms, and you can see that those are cuts into the density. So you can see that the density is mainly located between the 2 hydrogen atoms. So that's very nice. It's usually very pretty, and you can also see whether the crystal structure looks the way you expect to. So it's always a good practice to check the density by that way. You can also do the same using Cat3D, but for the wave function file, but then you have to select a band, a K point that you want to analyze. Okay, then we can go back to the tutorial. So here we have the density. It tells you that you can use the Kit3D binary file to analyze it. And then you can compute the atomization energy, which means the energy that you gain by putting the 2 hydrogen atoms close together in comparison with the 2 atoms being very far apart. So I will let you do that, and at the end you have the answer to the question of the first section. And that's it for this tutorial, so see you next time. Bye.